Hey there! How's it going? Thanks for joining me today. Whether you're relaxing at home, on your commute, or winding down for the evening, I'm really glad you're here. Tonight, I want to take you back to a moment that changed everything we thought we knew about our place in the cosmos. October 19th, 2017. Just after midnight, Hawaii time. The Haleakala Observatory sits perched on the rim of a dormant volcano. Its Pan-STARRS telescope methodically, sweeping the Pacific sky in its automated search for asteroids that might threaten Earth. Astronomer Robert Varick is reviewing the night's automated detections from his office at the University of Hawaii. Thousands of data points stream across his screen, the usual parade of known objects following predictable paths. But then something stops him cold. A faint dot of light moving across the star field at impossible speed. The numbers don't make sense. This object is racing through space at 26 kilometers per second, 4 times faster than any asteroid should be traveling. Varick runs the calculations again and again. The trajectory points to something that should be impossible, an object that didn't originate in our solar system. Within 6 hours, telescopes across the planet begin swiveling toward this cosmic intruder. The Canada-France-Hawaii telescope confirms the impossible velocity. The European Southern Observatory in Chile locks onto the target. The data streams in, and with each measurement, the impossible becomes undeniable. For the first time in human history, we've caught an interstellar visitor passing through our cosmic neighborhood. But here's the strange part. This discovery that should have been purely about orbital mechanics and gravitational physics quickly became something much more mysterious. Because Oumuamua, as it would come to be named, didn't behave like any natural object we'd ever observed. The scramble that followed was unlike anything astronomy had ever seen. Karen Meech at the University of Hawaii found herself leading an international effort as observatories worldwide dropped their planned observations. They had perhaps weeks, maybe only days, before this visitor would race beyond our ability to see it forever. What unfolded was a detective story played out in real time across multiple continents, where every new observation seemed to rewrite the textbook on what was possible in our universe. The first measurements revealed an object tumbling chaotically through space, completing one rotation every 7.3 hours. But as more data arrived, the shape that emerged was like nothing in our cosmic catalogue. Initial calculations suggested something elongated, perhaps 10 times longer than it was wide. Imagine a cosmic cigar racing through the darkness, or maybe a flat pancake spinning end over end. These aspect ratios simply don't exist among natural objects in our solar system. Our asteroids and comets are roughly spherical, maybe twice as long as they are wide at most. But Oumuamua appeared to be stretched into impossible proportions, and then there was its color, a deep reddish hue that spoke of eons spent wandering between the stars. This wasn't the fresh gray of recently formed space rock. This was something ancient, something that had been baking in cosmic radiation for millions, perhaps billions of years, as it journeyed from where exactly? The more telescopes focused on Oumuamua, the more questions multiplied. The Hubble Space Telescope managed to track its tumbling motion with unprecedented precision. Ground-based observatories captured spectra that revealed its surface composition, or rather, failed to reveal it in any way that made sense. Here's what we don't know. And it's staggering. We have no idea what Oumuamua is actually made of. The spectral data shows a surface unlike anything in our solar system. It's not rocky like an asteroid. It's not icy like a comet. It reflects light in a pattern that doesn't match any known material composition. But the real mystery, the one that would divide the scientific community and capture global imagination, was yet to come as Oumuamua swung around the sun and began its journey back to interstellar space. Something impossible happened. It accelerated, not the predictable acceleration from solar gravity, but an additional push that had no explanation. Marco Micheli's team at the European Space Agency measured it precisely. an extra acceleration of about 30 nanometers per second squared. That might sound tiny, but for an object drifting in the vacuum of space, it's enormous. It's like watching a mountain decide to change direction mid-flight. The first assumption was obvious: comet outgassing. When comets approach the sun, ice sublimates into vapor, creating jets that can push the comet slightly off course. This is normal physics, predictable physics. But there was a problem, a big one. No one could detect any sign of gas or dust around Oumuamua. Not a whisper, not a particle. Every telescope pointed at it saw the same thing: a solid object accelerating through space with no visible means of propulsion. The scientific community found itself facing something unprecedented. Here was an object that appeared to be violating Newton's laws of motion, in full view of humanity's most sophisticated instruments. The acceleration was real. Multiple independent teams confirmed it. But the mechanism remained completely invisible. Before we dive back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. This is where Oumuamua transformed from astronomical curiosity to genuine mystery. Teams of scientists began proposing increasingly exotic explanations. Maybe it was hydrogen ice, invisible to our telescopes, but capable of providing thrust as it sublimated. Maybe it was a fragment of solid nitrogen, like a chunk ripped from a Pluto-like world in another star system. And then Harvard astronomer Avi Loeb published a paper that sent shockwaves through the scientific community. His calculations showed that a thin artificial sail, perhaps a derelict piece of alien technology, could produce exactly the acceleration pattern they observed. The reaction was immediate and explosive. Colleagues accused Loeb of sensationalism. Others defended his right to explore all possibilities. The debate raged in academic journals, at conferences, and across social media. But beneath the controversy lay a deeper question that no one could answer. If Oumuamua wasn't a comet, wasn't an asteroid, and wasn't behaving like any natural object, what was it? The mystery deepened with every follow-up study. Attempts to detect radio signals came up empty. Searches for chemical signatures in the thin material it might be shedding found nothing. Even its exact shape remained uncertain. Different analysis methods produced different results. Some suggesting a cigar, others a pancake. Still others something entirely unprecedented. What made the situation even more extraordinary was the time pressure. Oumuamua was racing away from the sun at nearly 90,000 kilometers per hour, growing fainter by the day. By early 2018, it had become too dim for even our most powerful telescopes to track. Our window to study humanity's first confirmed interstellar visitor had slammed shut, leaving behind more questions than answers. But here's what haunts astronomers to this day. Oumuamua's visit revealed that our solar system isn't the isolated island we once thought it was. Statistical calculations suggest that at any given moment, roughly 10,000 objects like Oumuamua are passing through our cosmic neighborhood. We've been receiving interstellar mail for billions of years. We just didn't know how to read the return addresses. This realization has transformed how we think about planetary formation, the spread of life through the galaxy, and our place in the cosmic community. Every night, objects from other star systems slip through our solar system undetected. Some carry the chemical signatures of alien worlds. Others might harbor microscopic life protected in subsurface cracks. A few, if Loeb's hypothesis has any merit, might even be artificial. The story of Oumuamua's discovery is really the story of humanity's first conscious contact with the interstellar medium. For 4.6 billion years, Earth had been receiving visitors from other star systems. But October 19th, 2017, was the night we finally noticed. And what we noticed was something that doesn't fit any category we've created for understanding the cosmos. Something that accelerates without visible cause, that tumbles with chaotic precision, that reflects light in patterns we can't decode. Something that traveled for millions of years across the cosmic desert. just to briefly graze our attention before disappearing forever into the darkness between stars. Oumuamua taught us that the universe is stranger than we imagined, more connected than we believed, and full of mysteries that our current physics can't explain. It showed us that we live in a galaxy where interstellar objects regularly visit our solar system, carrying information from distant worlds we may never see. Most importantly, it demonstrated that we're not just passive observers of the cosmos, we're active participants in an ongoing conversation between star systems. The question is, are we ready to understand what the universe is trying to tell us? Tomorrow, we'll journey back millions of years to explore where Oumuamua might have come from and why its origin story might be even stranger than its visit. Because the path that brought our mysterious visitor to Earth involves cosmic pinball games, stellar nurseries, and journeys so long that entire civilizations could rise and fall while a single object drifts between the stars. Until then, keep looking up, because somewhere out there right now, the next interstellar messenger is already on its way. To understand where Oumuamua came from, we need to journey back in time. Not years or decades, but millions, perhaps billions of years into the cosmic past. Picture, if you will, a distant stellar system during its violent youth, when planets were still forming and gravitational chaos reigned supreme. This isn't speculation, it's the most likely scenario for how interstellar objects like Oumuamua begin their epic journeys. But here's what makes this story fascinating. We don't know which star system ejected our visitor, and the mechanics of how it happened reveal mysteries about planetary formation that we're only beginning to understand. The process starts in what astronomers call a stellar nursery, a dense cloud of gas and dust where multiple stars are born simultaneously. These cosmic neighborhoods are crowded places, with young stars orbiting dangerously close to one another. In our own solar system's youth, the Sun likely had stellar siblings, but they've long since drifted apart. Oumuamua's home system might still be intact, or it might have been completely destroyed by now. As planets form around these young stars, they don't settle into neat, stable orbits immediately. Instead, they migrate inward and outward, sometimes dramatically. Jupiter, in our own system, wandered much closer to the Sun before settling into its current orbit. During these migrations, smaller objects, asteroids, comets, planetary building blocks, get caught in a cosmic pinball game of gravitational encounters. Here's where the physics becomes both elegant and violent. When a small object passes too close to a giant planet, it receives what scientists call a gravitational slingshot. Most of these encounters result in the object either crashing into the planet, falling into the star, or settling into a stable orbit. But a tiny fraction, maybe 1 in 10,000, achieve something remarkable: escape velocity. Not just escape from the planet's gravity, but escape from the entire star system. The mathematics of this process are well understood, but the specifics of Oumuamua's ejection remain tantalizingly unknown. Computer simulations suggest it needed multiple gravitational encounters to reach interstellar speeds. Maybe it bounced between two giant planets like a cosmic billiard ball. Maybe it got caught in a three-body gravitational dance that flung it outward at tremendous velocity. What we can calculate is the energy required. To escape from a star system similar to ours, an object needs to reach speeds of at least 15 to 20 kilometers per second. Oumuamua was traveling at 26 kilometers per second when we found it, suggesting either a particularly violent ejection or additional acceleration along its journey. But here's the strange part. Tracing Oumuamua's path backward through time doesn't point to any obvious stellar origin. The object's trajectory, when reversed, passes through regions of space that are currently empty. Either its home star has moved significantly since the ejection, or Oumuamua's journey has been so long that stellar motions have erased the trail. This brings us to one of the most haunting aspects of Oumuamua's story: the sheer duration of its journey through interstellar space. Conservative estimates suggest it's been wandering between stars for at least several million years. More exotic calculations push that number into the hundreds of millions, possibly billions of years. Imagine the loneliness of such a voyage. For comparison, modern humans have existed for only about 300,000 years. L'Oumuamua began its journey when our species didn't exist, when the geography of Earth looked completely different, when the constellations held entirely different patterns. During this cosmic odyssey, Oumuamua traveled through what we euphemistically call empty space. But interstellar space isn't truly empty. It contains about 1 atom per cubic centimeter, mostly hydrogen, along with trace amounts of heavier elements and complex organic molecules. Over millions of years, this tenuous medium leaves its mark. The deep reddish color we observed on Oumuamua's surface tells the story of this journey. Cosmic rays, high-energy particles streaming through the galaxy, slowly cook the outer layers of any object exposed to interstellar space. They break apart surface molecules and create new chemical compounds that absorb blue light preferentially, leaving behind that characteristic red hue. This process, called space weathering, happens predictably. By studying Oumuamua's color and comparing it to laboratory experiments, scientists can estimate how long it's been exposed to the interstellar environment. The calculations suggest an exposure time of hundreds of millions of years at minimum, but what we don't know is even more fascinating than what we do. We don't know if Oumuamua has always been a single object, or if it's a fragment of something larger that broke apart during its journey. Collisions in interstellar space are extraordinarily rare, but over vast timescales, even rare events become probable. We don't know if its unusual shape is original or the result of some unknown process during its long voyage. Computer models of interstellar objects predict mostly spherical or slightly elongated forms. Oumuamua's extreme aspect ratio, possibly 10:1 length versus width, challenges our understanding of what shapes can survive million-year journeys through space. Most mysteriously, we don't know if Oumuamua experienced any other accelerations during its journey. That unexplained push we observed as it left our solar system might not have been unique. If similar accelerations occurred during its interstellar voyage, they could have significantly altered its trajectory, making its origin even more difficult to trace. The temperature story adds another layer of mystery. During its journey between stars, Oumuamua would have been incredibly cold, perhaps just a few degrees above absolute zero. At such temperatures, many materials become brittle and prone to fracturing. Others undergo phase transitions that could dramatically alter their properties. If Oumuamua contains exotic ices, hydrogen, nitrogen, or other volatile compounds, they would have been in states we rarely observe in laboratory conditions. These supercooled materials might explain some of its unusual behavior, but they also represent chemistry we don't fully understand. The journey itself might have been shaped by forces we haven't considered. Interstellar space contains magnetic fields, streams of charged particles, and radiation pressure from distant stars. Over millions of years, these subtle influences could accumulate into significant effects. Some theoretical models suggest that very small objects might actually be accelerated by starlight pressure during interstellar travel. Here's what particularly intrigues astronomers. Oumuamua's journey represents a form of information transfer between star systems. Its surface chemistry, internal structure, and even its unusual acceleration might carry encoded data about its origin system, a cosmic message, written in physics and geology, but decoding that message requires understanding processes that occur on timescales far beyond human experience. The stellar dynamics that ejected Oumuamua, the interstellar chemistry that modified its surface, the gravitational influences that shaped its trajectory, all of these operate on scales that challenge our ability to model and predict. Statistical studies suggest that objects like Oumuamua are created constantly throughout the galaxy. Every star system probably ejects thousands of objects during its formation and early evolution, This means the space between stars is filled with wandering ambassadors from distant worlds, each carrying unique information about their place of origin. The implications are staggering. If we could detect and study enough interstellar visitors, we might be able to map the chemical and physical properties of planetary systems throughout our local galactic neighborhood. We could learn about planet formation processes in environments completely different from our own solar system. Some scientists have proposed that interstellar objects might even carry biological information. Microorganisms protected in subsurface cracks could survive the journey between stars, potentially spreading life throughout the galaxy. Oumuamua's unusual properties make it an unlikely candidate for harboring life, but future visitors might tell a different story. The detection of Oumuamua also revealed how little we understand about the population of interstellar objects. Computer models predicted we should see one interstellar visitor every few decades. Instead, we found one within just a few years of developing the technology to detect them. This suggests either remarkable luck or fundamental gaps in our understanding of how common these objects really are. Recent calculations indicate that at any given moment, our solar system contains roughly 10,000 Oumuamua-sized objects from other star systems. They arrive constantly, most passing through undetected, carrying information from stellar neighborhoods we'll never visit. This realization transforms our perspective on planetary formation and evolution. Our solar system isn't an isolated laboratory where unique processes created unique conditions. Instead, it's part of a vast network of gravitational interactions and material exchange that spans the entire galaxy. Oumuamua's journey from another star isn't just an astronomical curiosity. It's evidence that the universe is more connected than we ever imagined. The building blocks of planets, the raw materials of life, even potentially life itself, might regularly migrate between star systems on journeys that span geological time. Tomorrow, we'll explore the physics that broke our understanding of what's possible. Because the real mystery of Oumuamua isn't where it came from. It's what happened when it tried to leave. The acceleration that defied Newton's laws and divided the scientific community represents one of the most profound puzzles in modern astronomy, and the answers we're still searching for might change everything we think we know about the universe. Here's where Oumuamua transforms from an interesting visitor into something that challenges the fundamental laws of physics as we understand them. What happened next split the scientific community down the middle and launched a debate that continues to this day as Oumuamua swung around the sun in late 2017 and began its journey back toward interstellar space. Astronomers expected it to follow a predictable path. Newton's laws of motion, refined by Einstein's general relativity, have never failed us when tracking objects in space. Comets, asteroids, spacecraft, everything follows the mathematical choreography of gravity with clockwork precision. But Oumuamua had other plans. Marco Micheli's team at the European Space Agency was meticulously tracking the object's trajectory, using the most precise measurements possible. They combined observations from multiple telescopes, accounting for every known force that could influence an object in space. Solar gravity, planetary perturbations, even the tiny pressure from sunlight, all factored into their calculations. The numbers that came back made no sense. Oumuamua was accelerating away from the sun at a rate of approximately 30 nanometers per second squared. That might sound impossibly small, but in the context of celestial mechanics, it's enormous. For a dead rock drifting through the vacuum of space, this acceleration is like watching a mountain spontaneously decide to change direction. The measurement was real. Multiple independent teams confirmed it using different telescopes and analysis methods. But the mechanism behind it remained completely invisible. The first assumption was obvious and reasonable: comet outgassing. When comets approach the sun, solar heat vaporizes subsurface ice, creating jets of gas and dust that can push the comet slightly off its predicted course. This rocket effect is well understood and easily detectable. Comets develop visible tails and leave measurable trails of debris as they shed material. But here's where Oumuamua shattered expectations. No one could find any evidence of outgassing whatsoever. The Spitzer Space Telescope, designed to detect the infrared signature of warm dust, saw nothing. Ground-based observatories searching for the spectral lines of vaporizing ice found empty spectra. Radio telescopes listening for the characteristic emissions of sublimating materials heard only silence. Every instrument trained on Oumuamua painted the same picture. A solid, apparently inert object somehow accelerating through space with no visible means of propulsion. This is where the scientific method both shines and struggles. Faced with an observation that contradicts established theory, scientists must either find flaws in the observation or expand the theory. The observation was rock solid. Multiple independent confirmations left no doubt about the acceleration. So the theory had to stretch, enter the exotic explanations. Darrell Seligman from the University of Chicago proposed one of the most intriguing possibilities: hydrogen ice. Unlike water ice or other volatile compounds, hydrogen ice sublimates at extremely low temperatures and produces gas that's essentially invisible to our telescopes. The hydrogen molecules are so light and spread out that they don't scatter light noticeably, and they don't emit detectable infrared radiation. This hypothesis was elegant because it solved the visibility problem. Hydrogen outgassing could provide the necessary thrust while remaining undetectable to current instruments. But it created new mysteries. How would solid hydrogen survive the journey from another star system? The material is so volatile that it should have sublimated away long before reaching our solar system. Seligman's models required specific thermal conditions that might occur only in certain types of interstellar environments. Oumuamua would need to have formed in an unusually cold region of space and maintained those temperatures throughout its journey. The physics work, but the probability seems extraordinarily low. Gregory Laughlin from Yale University proposed another possibility, a fragment of solid nitrogen. This scenario envisions Oumuamua as a chunk broken off from a Pluto-like object in another star system. Solid nitrogen can provide thrust as it sublimes, and under certain conditions, the outgassing might be difficult to detect. The nitrogen hypothesis explained not just the acceleration, but also Oumuamua's unusual shape. Computer models showed that a nitrogen iceberg exposed to stellar radiation would erode in specific patterns, potentially creating the elongated form we observed. The physics are sound, and the material properties match what we know about similar objects in our own solar system. But this explanation also required remarkable coincidences. The nitrogen would need to survive interstellar exposure for millions of years, retain its structural integrity during a chaotic tumbling journey, and begin sublimating at exactly the right rate when it reached our solar system. Then Avi Loeb from Harvard University published the paper that changed everything. Loeb's calculations were mathematically rigorous and scientifically sound. He showed that a thin, artificial light sail, perhaps just a few hundred meters across and less than a millimeter thick, could produce exactly the acceleration profile observed. Solar radiation pressure on such a structure would create the mysterious force that was pushing Oumuamua away from the sun. The implications were staggering. If Loeb was correct, humanity had just observed its first piece of alien technology. The scientific community's reaction was immediate and polarized. Colleagues accused Loeb of sensationalism and publicity seeking. Others defended his right to explore all possibilities, no matter how unconventional. The debate raged in academic journals, at conferences, and across social media platforms. But beneath the controversy lay a deeper issue that no one could resolve. If Oumuamua wasn't natural, what was it? Loeb's model suggested several possibilities. It could be a derelict light sail from an alien civilization, drifting through space like cosmic debris after its mission ended. It might be a piece of alien infrastructure, perhaps part of a larger structure that broke apart eons ago. Most intriguingly, it could be an active probe, though one that had either malfunctioned or was operating in ways we couldn't recognize. The light sail hypothesis explained not just the acceleration, but also Oumuamua's unusual shape and tumbling motion. A thin, flat structure would appear elongated when viewed edge-on and would tumble, chaotically, if it had been damaged or was designed for specific aerodynamic properties in an alien atmosphere. But the artificial origin theory created as many questions as it answered. Why would an alien civilization build light sails that looked exactly like natural objects? How would such technology survive the journey between star systems? And most importantly, why had we never detected anything like this before? The mystery deepened with every follow-up study. Radio telescopes searched for artificial signals, but found none. Attempts to detect chemical signatures of advanced materials came up empty. Even attempts to model the object's exact shape and composition produced contradictory results. Some analyses suggested a cigar-shaped object with an aspect ratio of 10:1. Others favored a flat, pancake-like structure. Still others proposed more exotic geometries, perhaps a fractal surface or a structure with internal cavities that affected its apparent density. What made the situation even more extraordinary was the accumulation of unusual properties. Oumuamua wasn't just accelerating without visible cause. It was also tumbling in a complex pattern that didn't match typical asteroid behavior. Its surface reflectivity was unusually uniform, lacking the variations expected from natural rock. Its trajectory showed subtle deviations that couldn't be explained by gravitational influences alone. Each anomaly by itself might have simple explanations. But the combination of all these unusual characteristics in a single object stretched the boundaries of coincidence. Here's what we still don't know, and it's what keeps astronomers awake at night. We have no definitive explanation for Oumuamua's behavior that accounts for all its observed properties. Every hypothesis requires either exotic materials, unlikely circumstances, or unknown physics. The hydrogen ice theory needs materials that shouldn't survive interstellar travel. The nitrogen fragment hypothesis requires extraordinary preservation over cosmic timescales. The artificial origin theory implies technologies we can't detect or understand. This uncertainty has transformed Oumuamua from an astronomical object into a philosophical challenge. It forces us to confront the limits of our knowledge and the assumptions built into our scientific models. Before we dive back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. The debate over Oumuamua's nature has also revealed deeper questions about how we approach extraordinary claims in science. The object clearly violated our expectations, but which explanation requires the smallest leap beyond established knowledge? Natural origins require exotic materials and unlikely preservation scenarios. Artificial origins require accepting that we've been visited by alien technology. Both possibilities stretch our current understanding, but in very different directions. Recent follow-up studies have added new layers to the mystery. Statistical analyses of Oumuamua's properties suggest it represents a completely new class of interstellar object. Computer simulations of planetary formation struggle to produce objects with its combination of characteristics. Even attempts to model its thermal properties during solar approach yield contradictory results. Some researchers have proposed hybrid explanations. Maybe Oumuamua is natural but composed of materials we haven't encountered before. Perhaps it's a type of object that forms only under specific conditions in certain stellar environments. Or it could be the product of processes we haven't yet discovered, natural phenomena that create artificial-looking structures. The most recent analyses using machine learning algorithms to search for patterns in Oumuamua's Observational data have identified subtle anomalies that weren't apparent in earlier studies. These AI systems, trained on thousands of known asteroid and comet observations, consistently flag Oumuamua as an outlier that doesn't fit any established category. What makes this particularly intriguing is that the anomalies aren't random. They show patterns that suggest underlying systematic causes. Either Oumuamua was shaped by processes we don't understand, or it was designed according to principles we haven't recognized. The physics that broke our brains goes beyond just Oumuamua's acceleration. It extends to fundamental questions about what's possible in the universe and how we recognize the difference between natural and artificial phenomena. If Oumuamua is natural, it reveals that planetary formation and interstellar evolution can create objects far stranger than we imagined. If it's artificial, it demonstrates that we're not alone in the universe and that alien technology might be more common than we assumed. Both possibilities are revolutionary. Both challenge our basic assumptions about cosmic processes and our place in the galaxy. And both remain equally plausible given our current understanding. The mystery of Oumuamua's physics isn't just about one unusual object. It's about the limits of scientific knowledge and the boundaries between the possible and impossible. It's a reminder that the universe still holds secrets that can shatter our most confident theories. Tomorrow, we'll explore what happened when Earth's astronomers realized they had only weeks to solve one of the greatest mysteries in the history of science. The hunt that followed mobilized telescopes across the planet and revealed just how much we don't know about detecting and studying visitors from other star systems, because Oumuamua wasn't just challenging our physics, it was racing away at 90,000 kilometers per hour, and every day made it fainter and more difficult to study. The clock was ticking, and the mystery was deepening with every observation. With Oumuamua racing away from the sun at nearly 90,000 kilometers per hour, Earth's astronomers found themselves in an unprecedented race against time. Every day that passed made the object fainter and more difficult to study. Every hour of delay meant losing precious photons that might hold the key to solving one of the greatest mysteries in astronomical history. The mobilization that followed was unlike anything the scientific community had ever attempted. Telescopes that had been booked months or years in advance suddenly became available as astronomers worldwide recognized the historic importance of this fleeting opportunity. Observing schedules were scrapped. Research programs were postponed. The entire global network of professional astronomy pivoted toward a single target, disappearing into the cosmic darkness. But here's what made this hunt so extraordinary. We weren't just trying to gather more data about a strange object. We were trying to determine whether humanity had just encountered evidence of alien technology. The Green Bank Telescope in West Virginia became the focal point of perhaps the most ambitious search for artificial signals ever attempted. As part of the Breakthrough Listen project, this massive radio dish, the world's largest fully steerable radio telescope, aimed its 100-meter aperture directly at Oumuamua. For 10 hours of continuous observation, the search covered billions of radio channels simultaneously, scanning frequencies from 1 to 12 gigahertz with unprecedented sensitivity. If Oumuamua was transmitting any signals, navigation beacons, status reports, or even unintentional electromagnetic leakage, the Green Bank Telescope would detect them. The result was deafening silence. But absence of evidence isn't evidence of absence, and the implications of that silence are more complex than they initially appear. If Oumuamua was artificial, it might be operating on frequencies we hadn't considered. It could be using communication methods we haven't discovered. Or it might simply be a derelict piece of technology, as silent as an abandoned spacecraft. The silence also doesn't rule out natural explanations. Most astronomical objects are radio quiet, producing no detectable emissions at the frequencies we typically monitor. The fact that Oumuamua wasn't broadcasting doesn't tell us definitively what it is, only what it isn't actively doing. Meanwhile, optical telescopes around the world scrambled for every possible observation. The Very Large Telescope in Chile's Atacama Desert turned its 8-meter mirrors toward the rapidly fading target. The twin Keck telescopes in Hawaii combined their light-gathering power to capture spectra that might reveal Oumuamua's composition. Even amateur astronomers with backyard telescopes contributed observations during those crucial final weeks. Each measurement added pieces to a puzzle that seemed to grow more complex rather than clearer. The Hubble Space Telescope, pushed to its absolute limits, managed to track Oumuamua's precise position and motion even as it became too faint for ground-based telescopes. These observations confirmed the mysterious acceleration and ruled out several proposed explanations. But what we couldn't detect became as important as what we could. No dust coma, no gas emissions, no debris trail, no thermal signature consistent with sublimating ice. Oumuamua appeared to be accelerating through space while shedding absolutely no detectable material. This absence of evidence created a new category of mystery. We were dealing with an object that behaved like a comet, accelerating away from the sun while looking like an asteroid, showing no signs of volatile material. It challenged our fundamental classification system for solar system objects. The shape analysis became increasingly sophisticated as more data arrived. Computer algorithms processed thousands of brightness measurements, tracking how Oumuamua's reflected light varied as it tumbled through space. The pattern that emerged was unlike anything in our astronomical databases. Initial models suggested extreme elongation, a cosmic cigar, perhaps 10 times longer than it was wide. But as the analysis became more refined, alternative interpretations emerged. Some models favored a flat, pancake-like structure. Others suggested more exotic geometries, perhaps a hollow shell or a structure with complex internal cavities. The tumbling motion itself added another layer of mystery. Oumuamua's rotation wasn't the simple spin expected from a natural object. Instead, it exhibited what astronomers call complex rotation, tumbling chaotically around multiple axes simultaneously. This type of motion typically results from violent collisions or structural instabilities. For a natural object, such chaotic tumbling might indicate a recent collision or a loose rubble pile held together by weak gravity. For an artificial object, it might suggest damage from interstellar travel or an intentional design feature we don't understand. The thermal observations added yet another puzzle. As Oumuamua approached the sun, it should have heated up predictably based on its size and distance. But the thermal emissions detected by infrared telescopes didn't match the expected patterns for any known type of object. The heating curve was too flat for solid rock, too steep for metallic composition, and showed variations that couldn't be explained by simple rotation. Either Oumuamua had unusual thermal properties, or its surface was more complex than our models assumed. Spectroscopic analysis, the technique that reveals an object's chemical composition. By examining how it absorbs and reflects different wavelengths of light, produced equally puzzling results. The spectrum wasn't quite like any asteroid class we'd catalogued. It wasn't quite like any comet we'd studied. It occupied a unique region of parameter space that didn't correspond to any known solar system material. This spectral signature became a crucial piece of evidence in the ongoing debate about Oumuamua's nature. Natural formation processes typically produce predictable chemical signatures based on temperature, pressure, and available elements during formation. Oumuamua's spectrum suggested either exotic formation conditions or materials we hadn't encountered before. The polarization measurements added another dimension to the mystery. When light reflects off an object's surface, it becomes polarized in patterns that reveal information about surface texture, composition, and structure. Oumuamua's polarization signature was inconsistent with typical asteroid surfaces, suggesting either unusual material properties or a surface texture unlike anything in our solar system. As the observational campaign intensified, Patterns began emerging that challenged every proposed explanation. The acceleration wasn't constant. It varied in ways that didn't match simple outgassing models. The brightness variations weren't perfectly periodic. They showed subtle irregularities that suggested structural complexity. The thermal behavior wasn't uniform, different. Parts of the object seemed to have different thermal properties. Each new measurement eliminated some possibilities while opening others. The hydrogen ice hypothesis struggled to explain the thermal observations. The nitrogen fragment theory couldn't account for the spectral properties. The artificial origin hypothesis faced the challenge of explaining why advanced technology would tumble so chaotically. Here's what particularly frustrated astronomers. Oumuamua seemed designed to confound analysis. Its rapid rotation made detailed surface mapping impossible. Its small size pushed telescopes to their detection limits. Its trajectory carried it quickly beyond optimal observing angles. Even its timing seemed calculated to maximize mystery, arriving when our detection capabilities were just barely sufficient to see it, but not quite advanced enough to study it thoroughly. The international collaboration that emerged during this period was unprecedented in astronomy. Telescopes in Chile shared data with facilities in Hawaii. European observers coordinated with American teams. Even competing research groups pooled their observations and analysis techniques. The urgency of the situation forced the normally deliberate pace of scientific research into overdrive. But despite this massive coordinated effort, fundamental questions remained unanswered. By early 2018, Oumuamua had faded beyond the detection threshold of even our most powerful telescopes. Our window of opportunity had closed, leaving behind more questions than answers. The final observations captured Oumuamua as little more than a faint point of light, indistinguishable from background stars, except for its motion. Teams squeezed every possible piece of information from these last photons, using advanced mathematical techniques to extract signals from noise. These final measurements confirmed that Oumuamua remained anomalous to the very end. Its acceleration continued even as it moved away from the Sun, ruling out several temperature-dependent explanations. Its rotation showed no signs of the damping expected from gas emission. Its trajectory maintained subtle deviations that couldn't be explained by known gravitational influences. What we learned during those intense months of observation is that the universe contains objects that don't fit our existing categories. Oumuamua forced us to confront the possibility that our classification systems, natural versus artificial, comet versus asteroid, familiar versus exotic, might be inadequate for describing what's actually out there. Before we dive back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. The hunt for Oumuamua's secrets revealed as much about our limitations as observers as it did about the object itself. We discovered that even with humanity's most advanced telescopes and analysis techniques, some mysteries remain tantalizingly beyond our reach. But the effort also demonstrated something remarkable about human curiosity and scientific cooperation. Faced with an unprecedented mystery, the global astronomical community set aside competitive instincts and worked together with a focus rarely seen in academic research. The shared recognition that we might be studying humanity's first confirmed interstellar visitor, or possibly our first encounter with alien technology, created a sense of urgency that transcended normal scientific boundaries. The observational techniques developed during the Oumuamua campaign have revolutionized how we study small, rapidly moving objects. New algorithms for extracting signals from noisy data, improved methods for coordinating observations across multiple telescopes, and enhanced techniques for analyzing complex rotation patterns all emerged from the urgent need to understand our mysterious visitor. These technological advances are already paying dividends. The next interstellar object, when it arrives, will face a detection and analysis network far more sophisticated than what was available in 2017. We've learned from our first encounter and are preparing for the next one. But perhaps the most important lesson from the hunt for Oumuamua's secrets is how much we still don't know about our own cosmic neighborhood. The object's detection revealed that interstellar visitors are more common than we expected, more diverse than we imagined, and potentially more significant than we dared hope. The silence from our radio searches doesn't close the book on artificial origins. It simply adds another constraint to the growing list of Oumuamua's unusual properties. Future interstellar visitors might be more cooperative, broadcasting signals we can detect or displaying behaviors that clearly indicate their nature. The spectral and thermal puzzles highlight gaps in our understanding of how materials behave under extreme interstellar conditions. Laboratory experiments and computer simulations are now being designed to test whether natural processes can create objects with Oumuamua's combination of properties. Most significantly, the hunt intensified our awareness that we live in a dynamic galactic environment where objects regularly travel between star systems. Oumuamua wasn't just a curious visitor. It was our first glimpse into a vast population of interstellar wanderers that we're only beginning to detect and understand. Tomorrow, we'll explore one of the most thought-provoking questions raised by Oumuamua's mysterious properties. What would happen if our enigmatic visitor suddenly exploded? The answer reveals not just the secrets that explosion might unveil, but also how such an event would transform our understanding of interstellar objects and potentially revolutionize our approach to studying visitors from other star systems. Because sometimes the most profound scientific discoveries come not from what we observe, but from imagining what we might learn if the universe gave us one more unexpected opportunity to peek behind the cosmic curtain. Imagine this scenario. Tomorrow morning, astronomers at the Catalina Sky Survey detect an unexpected flash from the direction where Oumuamua disappeared into the cosmic darkness. Within minutes, automated alert systems notify observatories worldwide. The first reports are tentative, a brief brightening in a region of space where no known object should exist. But as more telescopes confirm the observation, the impossible becomes undeniable. Our mysterious interstellar visitor has exploded. This thought experiment isn't idle speculation. It's a window into one of the most profound questions in modern astronomy. What secrets would Oumuamua's destruction reveal, and how would such an event transform our understanding of interstellar objects forever? The first challenge would be confirming that the explosion actually came from Oumuamua. By now, the object is racing through space more than 20 astronomical units from the Sun, beyond the orbit of Uranus and growing more distant by the hour. At such extreme range, even our most powerful telescopes would struggle to detect debris from a small object's destruction. But the explosion's light signature would tell a story unlike anything we've ever observed. The spectrum of that flash, the rainbow of colors created as different materials vaporize and emit characteristic wavelengths, would finally reveal what Oumuamua was actually made of. If the explosion showed silicon and iron emission lines, we'd know we were dealing with rocky material similar to asteroids in our own solar system. If we detected water vapor and carbon compounds, it would suggest icy composition, more like a comet. But if the spectrum revealed exotic materials, perhaps unusual isotope ratios or elements that don't occur naturally in our solar system, we'd be facing evidence of formation processes we don't understand. The most intriguing possibility is what we might not detect. If Oumuamua was Avi Loeb's hypothetical light sail, the explosion might show a spectrum dominated by lightweight elements arranged in patterns that don't occur in nature. Artificial materials often have isotope ratios that differ from natural. Processes and their thermal signatures during destruction can reveal manufacturing techniques and structural designs. But here's where the scenario becomes even more fascinating. The explosion would create a debris cloud expanding at kilometers per second, and each fragment would carry information about Oumuamua's internal structure. For the first time, we might be able to study the interior composition of an interstellar object instead of just its surface. The debris analysis would require a complete mobilization of Earth's astronomical resources. Every major telescope would pivot toward the expanding cloud, racing to capture spectra before the fragments dispersed beyond detection. Radio telescopes would search for emission lines from exotic molecules. Infrared observatories would track the thermal evolution of different debris components. The timing would be critical. Different materials vaporize at different temperatures, creating a temporal sequence of spectral signatures. Lightweight elements would appear first, followed by progressively heavier compounds as the explosion energy dissipated. By analyzing this sequence, scientists could reconstruct not just Oumuamua's composition, but also its internal structure. Which materials were on the surface, which were buried deep inside, and how they were arranged. If Oumuamua contained exotic ices like the hydrogen or nitrogen proposed in various theories, the explosion would finally provide definitive proof. These materials would create distinctive spectral signatures impossible to miss in a high-energy vaporization event. We'd know within hours whether any of the natural explanations for its mysterious acceleration were correct. The explosion's energy signature would reveal equally important information. A natural object, perhaps an ancient comet with unstable internal structure, would explode in predictable ways based on its size and composition. The energy release would follow patterns we've observed in laboratory experiments and computer simulations, but an artificial object might explode very differently. Advanced materials could release stored energy in unusual patterns. Structural components might vaporize in sequences that reveal engineering design. Even the explosion's symmetry could indicate whether Oumuamua was a natural formation or a constructed object. The debris cloud's expansion pattern would provide another crucial piece of evidence. Natural explosions typically create roughly spherical debris patterns, with variations based on the object's rotation and internal structure. But if Oumuamua was indeed a flat light sail or some other artificial construct, the debris might expand in highly asymmetrical patterns that reflect its original geometry. Here's what makes this scenario particularly compelling. The explosion would solve some mysteries while creating entirely new ones. Even if we definitively determined Oumuamua's composition and structure, we'd still face profound questions about how such an object came to exist and why it was traveling through our solar system. If the explosion revealed natural materials arranged in impossible configurations, we'd need to revise our understanding of planetary formation processes. If it showed artificial signatures, we'd face the staggering implications of confirmed contact with alien technology. Either outcome would be revolutionary. The scientific mobilization that would follow such an explosion would dwarf even the intense observation campaign of 2017. Emergency funding would flow to fast-track analysis programs. Space agencies would immediately begin planning intercept missions to collect actual debris samples. The fragments might remain detectable for years, giving us unprecedented opportunity to study interstellar material in detail. Some debris might even be traveling slowly enough for spacecraft to catch. Unlike Oumuamua's hyperbolic trajectory that carried it quickly beyond our reach, explosion fragments would spread out at various velocities. The slowest pieces might remain within range of specially designed intercept missions launched years from now. The implications cascade beyond just understanding one mysterious object. Oumuamua's explosion would provide our first detailed look at how materials behave during interstellar travel. We'd learn about radiation damage, temperature cycling, and chemical evolution over cosmic timescales. This information would be crucial for understanding the entire population of interstellar objects we're now beginning to detect. If the explosion revealed exotic materials or artificial signatures, it would trigger the most intensive scientific investigation in human history. Every fragment would be precious, carrying information about technologies or formation processes beyond our current understanding. The debris analysis would likely take decades and spawn entirely new fields of research, but perhaps the most profound impact would be philosophical. Oumuamua's explosion would force humanity to confront definitive answers about our place in the universe. If natural, it would reveal that cosmic evolution can create objects far stranger than we imagined. If artificial, it would confirm that we're not alone, and that advanced civilizations have technologies we can barely comprehend. The explosion scenario also highlights how much we've learned from Oumuamua's brief visit. The observational techniques, analysis methods, and international cooperation networks developed during our first encounter with an interstellar object would be crucial for studying the debris. We're far better prepared now for analyzing unusual cosmic phenomena than we were in 2017. Before we dive back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. The debris collection possibilities represent perhaps the most exciting aspect of this hypothetical scenario. For the first time in human history, we might have the opportunity to bring actual interstellar material back to Earth for laboratory analysis. The fragments would be precious beyond measure, each piece a messenger from another star system carrying information we could never obtain through telescopic observation. Alone, laboratory analysis of interstellar debris would reveal isotope ratios that could identify the specific type of star system where Oumuamua formed. Different stellar environments create distinctive chemical signatures, and these cosmic fingerprints would survive the journey between star systems. We might finally learn not just that Oumuamua came from another star, but which type of star, and possibly even which stellar neighborhood. The mineral structures would tell stories about formation temperatures, pressures, and chemical environments completely different from anything in our solar system. If Oumuamua formed around a more massive star, a binary system, or in a region with unusual heavy element abundances, those conditions would be recorded in its crystalline structure like pages in a cosmic library. Even more intriguingly, the debris might contain complex organic molecules that survived the interstellar journey. These wouldn't necessarily indicate life, but they would reveal the chemical complexity possible in other stellar environments. We might discover molecular structures that don't form naturally in our solar system, expanding our understanding of cosmic chemistry. If Oumuamua was artificial, the laboratory analysis would be even more revolutionary. We'd have actual samples of alien technology to study with every analytical technique available to materials science. The molecular structures, isotope engineering, and manufacturing techniques would provide insights into how another civilization approaches materials engineering and spacecraft design. The explosion scenario also reveals how unprepared we currently are for such an event. Our deep space monitoring networks are designed to track objects, not analyze explosive events at extreme distances. The radio telescope arrays, optimized for searching cosmic phenomena, aren't necessarily configured for rapid response to sudden, brightening events in specific sky coordinates. But this hypothetical disaster would drive rapid technological development. New instruments specifically designed for analyzing interstellar debris would emerge. Improved coordination protocols between observatories would be implemented. Enhanced computer models for predicting debris evolution would be developed. The international legal and political implications would be equally profound. If the debris contained artificial materials, questions of ownership, study rights, and information sharing would arise. Which nations or organizations would have access to potentially alien technology? How would the analysis results be distributed? These questions would challenge existing frameworks for managing scientific discoveries with global implications. The explosion would also accelerate the search for additional interstellar objects. Knowing that Oumuamua was either composed of exotic natural materials or artificial technology would intensify efforts to detect and study future visitors. The Vera Rubin Observatory and other next-generation detection systems would operate with new urgency, scanning the skies for objects that might provide follow-up evidence. Most significantly, Oumuamua's hypothetical explosion would transform it from an unsolved mystery into a Rosetta Stone for understanding interstellar phenomena. The debris analysis would provide ground truth for testing theories about planetary formation, interstellar chemistry, and possibly even alien technology. The scenario ultimately illustrates how much scientific potential remains locked within mysteries we can't currently solve. Oumuamua disappeared before we could answer fundamental questions about its nature, but its hypothetical destruction would reveal secrets that might reshape our understanding of the universe. Sometimes, the most profound discoveries come not from successful missions, but from unexpected events that force us to see familiar phenomena in entirely new ways. Oumuamua's explosion would be such an event, a cosmic accident that accidentally solved one of astronomy's greatest puzzles while opening entirely new frontiers for exploration and understanding. Tomorrow, we'll explore how Oumuamua's brief visit has already begun, transforming our approach to detecting and studying interstellar objects. The technologies, techniques, and international cooperation networks emerging from our first encounter are preparing us for a future where interstellar visitors are routine rather than extraordinary, and where we might finally get the answers that are mysterious first. Contact left tantalizingly beyond our reach. Oumuamua's brief passage through our solar system didn't just leave us with unsolved mysteries. It sparked a technological revolution that's reshaping how we explore the cosmos. The frustration of watching our first confirmed interstellar visitor disappear before we could properly study it has driven innovations that will ensure we're ready for the next encounter, and there will be a next encounter. The question isn't if, but when. The Vera Rubin Observatory, currently under construction in Chile's Atacama Desert, represents the most ambitious sky survey ever attempted. When it becomes fully operational, this facility will detect interstellar objects not once per decade, as we've experienced so far, but potentially monthly. Its 8.4 billion pixel camera will photograph the entire visible sky every few nights, creating a time-lapse movie of the universe that captures everything in motion. But here's what makes the Rubin Observatory truly revolutionary. It's designed specifically to catch objects like Oumuamua while they're still approaching our solar system, rather than discovering them on their way out. The advance warning could give us years to prepare, instead of the desperate weeks we had. With our first interstellar visitor, the detection algorithms running on Rubin's data streams have been trained on Oumuamua's unique characteristics. Machine learning systems now know what to look for: objects moving too fast for solar system origin, trajectories that don't close into elliptical orbits, acceleration patterns that don't match known gravitational influences. These AI sentinels scan millions of observations nightly, flagged to recognize the subtle signatures of interstellar travelers. But detection is only the beginning. The real revolution lies in what we're building to study these objects once we find them. Project Lyra represents one of the most audacious mission concepts ever proposed. Named after the constellation containing Vega, one of Oumuamua's potential destination stars, this mission would use advanced solar sail technology to actually chase down future interstellar objects. Unlike conventional spacecraft that rely on chemical propulsion, solar sails can achieve the extreme velocities necessary to match course with objects traveling at interstellar speeds. The engineering challenges are staggering. The spacecraft would need to survive accelerations that would destroy conventional satellites. It would require autonomous navigation systems capable of course corrections across distances where radio communication with Earth takes hours. Most critically, it would need instruments robust enough to function after years of interstellar flight through radiation and micrometeorite impacts. But the potential payoffs are equally staggering. Instead of observing interstellar objects from hundreds of millions of kilometers away, Project Lyra would enable close-up study from distances measured in hundreds of meters. We could map surface features, analyze composition with unprecedented precision, and even attempt to collect samples for eventual return to Earth. The European Space Agency has taken a different approach with their Comet Interceptor mission, currently positioned at the L2 Lagrange point, a gravitational parking spot about 1.5 million kilometers from Earth. This spacecraft waits in standby mode, ready to sprint toward any interesting object that appears in our cosmic neighborhood. What makes Comet Interceptor particularly intriguing is its modular design. The main spacecraft carries smaller probes that can be deployed for different types of encounters. Some modules are designed for high-speed flybys that capture data during brief encounters. Others could attempt soft landings on slowly rotating objects. One concept even includes an impactor designed to create artificial craters that would expose subsurface materials for analysis. The mission architecture acknowledges a crucial lesson from Oumuamua. We need to be ready for objects that don't behave like anything we've studied before. The modular approach allows mission planners to adapt their strategy based on what they actually encounter rather than what they expect to find. But perhaps the most ambitious concepts involve missions that wouldn't just study interstellar objects, they would intercept them. The breakthrough that makes this possible comes from advances in ion propulsion and solar sail technology. Next-generation spacecraft could achieve velocities that seemed impossible just a decade ago. Combined with improved targeting algorithms and autonomous navigation, these vehicles could potentially match velocity with interstellar objects and ride alongside them for extended periods. Imagine a spacecraft that latches onto an interstellar visitor and travels with it for months or years, continuously collecting data as the object journeys back toward interstellar space. Such a mission could monitor how the object's properties change as it moves away from solar heating, track any ongoing acceleration or outgassing, and even observe how it responds to the transition back to the interstellar medium. The technical challenges are immense, but so are the potential discoveries. We might finally answer the fundamental questions that Oumuamua left unresolved. What are these objects made of? How do they form? Where do they come from? And most provocatively, could any of them be artificial? The detection infrastructure is evolving just as rapidly as the mission concepts. Ground-based telescopes are being equipped with rapid response systems that can automatically begin detailed observations within minutes of detecting a potential interstellar object. Space-based platforms offer the advantage of continuous monitoring without atmospheric interference. The James Webb Space Telescope, despite being primarily designed for distant galaxy observations, has proven remarkably capable of studying small solar system objects. Its infrared sensitivity could detect thermal emissions from interstellar visitors that remain invisible to optical telescopes. Future space telescopes designed specifically for solar system monitoring could spot interstellar objects years before they reach their closest approach to the Sun. But the most significant infrastructure development might be the international coordination networks that are emerging from the Oumuamua experience. The urgent need to share observations and coordinate analysis during our first interstellar encounter revealed gaps in how the global astronomical community responds to time-critical discoveries. New protocols now exist for rapidly sharing observational data across institutions and national boundaries. Automated alert systems can notify relevant teams within minutes of a significant detection. Telescope time allocation procedures have been streamlined to enable rapid response observations. without the months-long approval processes that normally govern major facilities. These coordination improvements extend beyond just interstellar objects. The systems developed for Oumuamua response are already being used to coordinate observations of potentially hazardous asteroids, unusual comets, and other time-sensitive astronomical phenomena. The amateur astronomy community has also been mobilized in unprecedented ways. Distributed computing projects now enlist thousands of citizen scientists in the search for interstellar objects. Advanced amateur telescopes contribute observations that supplement professional facilities. Even smartphone apps allow enthusiasts to participate in real-time analysis of unusual objects. This democratization of interstellar object research means that the next Oumuamua might be discovered not by a professional observatory, but by a dedicated amateur astronomer scanning the skies from their backyard. The global network of observers has expanded exponentially since 2017. The data analysis techniques have advanced just as dramatically as the detection methods. Machine learning algorithms trained on Oumuamua's characteristics can now identify subtle patterns in observational data that human analysts might miss. These AI systems can process thousands of potential detections simultaneously, flagging only the most interesting candidates for detailed human review. But perhaps more importantly, the analysis software has been designed to recognize when objects don't fit existing categories. Instead of forcing unusual observations into familiar classifications, the new systems are programmed to identify genuine anomalies and highlight them for special attention. The laboratory capabilities for analyzing interstellar materials have also expanded significantly. New mass spectrometry techniques can identify isotope ratios with unprecedented precision. Advanced microscopy can examine material structures at the molecular level. Even theoretical capabilities for studying exotic matter have improved as physicists develop new models for materials that might exist only under interstellar conditions. These advances are already paying dividends. When the second confirmed interstellar object, Comet Borisov, was detected in 2019, the response was swift and coordinated. Multiple telescopes tracked it for months. Spacecraft missions were proposed for future encounters, and detailed composition analysis was completed before the object faded from view. Importantly, Comet Borisov behaved much more like a typical comet than Oumuamua did. It showed clear signs of outgassing, developed a visible tail, and followed predictable trajectories based on gravitational forces alone. This normal behavior actually made Oumuamua's anomalies even more significant by demonstrating that interstellar objects can behave conventionally when they're composed of familiar materials. Before we dive back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. The contrast between these two interstellar visitors has shaped how we're preparing for future encounters. We now know that interstellar objects span a wide range of properties, from conventional icy comets like Borisov to mysterious accelerating objects like Oumuamua. Our detection and study systems need to be prepared for this entire spectrum of possibilities. The mission concepts under development reflect this diversity. Some spacecraft are optimized for studying conventional cometary behavior. Others are designed specifically to investigate objects showing anomalous properties. A few are equipped with instruments capable of detecting artificial materials or structured surfaces that might indicate technological origin. The most ambitious future missions would go beyond just studying individual interstellar objects. Advanced concepts involve establishing permanent monitoring stations at the edge of our solar system, robotic sentinels, that could detect and begin analyzing interstellar visitors years before they become visible from Earth. These deep space monitoring platforms would solve one of the fundamental challenges revealed by Oumuamua: The objects spend most of their time too far from the Sun for detailed study from Earth-based telescopes. By positioning instruments closer to their trajectories, we could extend the observation window from weeks to years. The technology requirements for such missions push the boundaries of current capabilities. The spacecraft would need to operate autonomously for decades in the harsh environment of deep space. They would require power systems that function far from solar energy. Most challengingly, they would need to transmit detailed scientific data across distances where radio signals take hours to reach Earth. But the scientific potential is extraordinary. Deep space monitors could detect patterns in interstellar object arrival rates, compositions, and trajectories that might reveal large-scale processes occurring throughout the galaxy. We might discover that certain types of objects arrive preferentially from specific directions, suggesting systematic ejection processes from stellar nurseries or mature planetary systems. The infrastructure we're building extends beyond just hardware and software to include new international cooperation frameworks. The recognition that interstellar objects are a global scientific resource has led to unprecedented agreements for sharing data, coordinating observations, and jointly funding ambitious missions. These frameworks acknowledge that no single nation or institution has the resources to fully investigate interstellar visitors. The objects arrive unpredictably, remain observable for limited time periods, and require diverse expertise spanning multiple scientific disciplines. International cooperation isn't just beneficial, it's essential. The educational and outreach components represent another crucial element of our preparation for future encounters. The public fascination with Oumuamua demonstrated enormous interest in interstellar objects and their implications for understanding our place in the universe. This enthusiasm is being channeled into educational programs that prepare the next generation of scientists and engineers for careers in interstellum. Research universities are establishing new degree programs focused specifically on interstellar phenomena. Research institutions are creating interdisciplinary centers that bring together astronomers, planetary scientists, engineers, and even experts in astrobiology and artificial intelligence. The field of interstellar object research is evolving from a niche specialty into a major scientific discipline. The technological revolution sparked by Oumuamua extends far beyond just studying interstellar visitors. The detection algorithms, rapid response protocols, and international coordination systems are being adapted for monitoring potentially hazardous asteroids, tracking space debris, and even searching for signs of extraterrestrial intelligence. The advances in autonomous spacecraft technology required for interstellar intercept missions are driving innovations in robotic exploration throughout the solar system. The improved data analysis techniques developed for processing unusual observational signatures are enhancing our ability to study conventional astronomical objects. Most significantly, the infrastructure we're building acknowledges that we now live in a universe where interstellar visitors are expected rather than extraordinary. The detection of Oumuamua and Comet Borisov within just 2 years suggests that interstellar objects may be far more common than we previously imagined. Statistical models now predict that we might detect dozens of interstellar objects per year once the Vera Rubin Observatory reaches full operation. Each detection will be an opportunity to learn something new about planetary formation, stellar evolution, and the distribution of materials throughout the galaxy. We're transforming from passive observers of occasional cosmic visitors into active participants in systematic interstellar research. The future we're building doesn't just prepare us to study the next Oumuamua, it positions us to understand the entire population of objects, traveling between star systems and the wealth of information they carry about cosmic processes we can't observe any other way. Tomorrow, we'll explore how this new understanding of interstellar visitors is fundamentally changing our perspective on the universe itself. Because Oumuamua didn't just visit our solar system, it opened our eyes to a cosmos far more dynamic, connected, and mysterious than we ever imagined possible. Before October 19th, 2017, our solar system felt like an island, an isolated collection of planets, moons and debris orbiting peacefully in the cosmic void. We knew intellectually that we were part of a vast galaxy containing hundreds of billions of stars, but that knowledge felt abstract, disconnected from our daily astronomical reality. Oumuamua changed everything. Now we know our solar system is more like Grand Central Station than a remote island. Objects from other star systems pass through constantly, carrying information from distant worlds we may never visit. At any given moment, statistical calculations suggest roughly 10,000 Oumuamua-sized objects are racing through our cosmic neighborhood on journeys that span millions of years and countless star systems. This revelation has fundamentally transformed how we think about planetary formation, the distribution of life throughout the galaxy, and our place in the cosmic community. The implications cascade through every branch of astronomy and planetary science, forcing us to rewrite textbooks and reconsider assumptions we've held for decades. Consider what this means for understanding how planets form. For billions of years, we assumed that each star system developed in isolation, using only the materials present in its original stellar nursery. The building blocks of Earth, the iron in our blood, the carbon in our DNA, the water in our oceans, all came from the disk of gas and dust that surrounded the young sun. But Oumuamua's visit revealed that planetary formation isn't an isolated process. Star systems regularly exchange materials through interstellar objects ejected during their chaotic early years. Earth might contain elements forged in the nuclear furnaces of distant stars, delivered by interstellar visitors that arrived when our planet was still forming. This interstellar contamination could explain some puzzling features of our solar system's composition. Unusual isotope ratios in meteorites, unexpected chemical signatures in ancient rocks, even the distribution of water and organic compounds throughout the solar system might reflect contributions from objects that originated around other stars. The implications extend far beyond just chemistry. If biological materials can survive interstellar journeys protected within subsurface cracks, then life itself might migrate between star systems. Microorganisms that evolved around one star could seed planetary formation around another, creating a galactic web of biological exchange that operates on timescales far longer than individual civilizations. This concept, called panspermia, was once considered pure speculation, but Oumuamua's detection proves that the transportation mechanism exists. Objects do travel between star systems. The question is no longer whether interstellar migration is possible, but how often it occurs and what survives the journey. Laboratory experiments have shown that certain extremophile bacteria can survive conditions similar to interstellar space for extended periods. Protected from radiation by just a few centimeters of rock or ice, these organisms could potentially maintain viability during million-year journeys between stars. If life is common throughout the galaxy, it might be far more connected than we ever imagined, but the biological implications pale beside the technological possibilities that Oumuamua has forced us to consider. Avi Loeb's artificial origin hypothesis, regardless of whether it's correct for our first interstellar visitor, opened a door that can never be fully closed. We now know that detecting alien technology is possible, and we're actively developing the instruments and techniques to recognize it. This represents a profound shift in how we approach the search for extraterrestrial intelligence. Instead of focusing solely on radio signals or optical beacons, we're now scanning for physical artifacts that might pass through our solar system. Advanced civilizations might use interstellar objects as transportation, communication relays, or scientific probes designed to study other star systems. The statistical implications are staggering. If even a tiny fraction of interstellar objects are artificial, perhaps 1 in a million, then we should expect to encounter obvious alien technology within the next few decades as our detection capabilities improve. The Vera Rubin Observatory alone will discover thousands of interstellar objects during its operational lifetime. But here's what makes Oumuamua's legacy particularly profound. It taught us that the universe doesn't necessarily announce its most important secrets with obvious fanfare. Our first potential encounter with alien technology didn't involve dramatic radio signals or massive starships. Instead, it looked like a tumbling piece of cosmic debris that happened to accelerate in ways we couldn't explain. This subtlety has transformed how we think about detecting artificial phenomena in space. Advanced alien technology might be designed to appear natural, either for camouflage or simply because effective engineering converges on solutions that mimic natural processes. The signatures we should be looking for might be statistical rather than obvious, patterns that emerge only when we study large numbers of objects. The cultural and philosophical impacts ripple outward in waves we're still discovering. Children growing up today live in a universe where interstellar visitors are confirmed reality rather than science fiction speculation. This knowledge shapes how they think about cosmic processes, planetary evolution, and the possibility of life elsewhere in the galaxy. Science fiction has been transformed too. Authors and filmmakers no longer need to invent exotic mechanisms for interstellar travel or contact. The universe has provided real examples of objects that journey between star systems, carrying information and potentially life itself across cosmic distances. The boundary between scientific fact and imaginative speculation has shifted in ways that inspire entirely new stories about our place in the cosmos. Research funding has responded to this transformed perspective. Universities are establishing new departments focused on interstellar studies. Government agencies are allocating resources toward detecting and analyzing visitors from other star systems. International organizations are developing protocols for sharing data about objects that might represent humanity's first contact with alien technology. The transformation extends beyond just academic and government institutions. Private space companies are proposing missions to intercept future interstellar objects. Amateur astronomers are contributing to detection efforts through citizen science projects. Even smartphone apps now allow enthusiasts to participate in real-time analysis of potentially interstellar phenomena. But perhaps the most significant change is psychological. We now scan the skies not just to catalog what's out there, but to catch the next messenger from another star. Every unusual object, every unexpected trajectory, every anomalous acceleration pattern might be our next glimpse into cosmic processes we don't understand or technologies we can't yet. Imagine this vigilant anticipation has created a new form of cosmic awareness. We're living through the early years of what historians might call the interstellar age, a period when humanity first became conscious participants in the galactic exchange of materials, information, and possibly life itself. The mathematical models that govern our understanding of galactic evolution have been revolutionized by Oumuamua's implications. Computer simulations now include interstellar contamination as a standard feature of planetary system formation. The chemical evolution of galaxies must account for materials that migrate between star systems over cosmic time. Even our understanding of stellar neighborhoods has changed. Stars don't just influence each other through gravity, they exchange physical materials through objects like Oumuamua that carry chemical and potentially biological information across interstellar distances. The galaxy is more interconnected than we ever suspected. The technological challenges of studying interstellar objects have driven innovations that benefit all of astronomy. The rapid response protocols developed for Oumuamua observations are now used for studying supernovae, gamma-ray bursts, and other time-sensitive phenomena. The international cooperation frameworks have improved. how we coordinate observations of everything from potentially hazardous asteroids to distant galaxies. The data analysis techniques required to extract maximum information from brief observational windows have enhanced our ability to study all types of astronomical objects. Machine learning algorithms trained to recognize unusual patterns in Oumuamua's data are now being applied to searches for exoplanets, dark matter signatures, and gravitational wave sources. Most importantly, Oumuamua taught us that the universe is stranger than we imagined and more generous with its secrets than we dared hope. Every clear night brings the possibility of another interstellar visitor, another cosmic messenger carrying information from stellar neighborhoods we'll never see. The next detection might come tonight. It could be announced tomorrow morning. The algorithms are running constantly, scanning millions of observations for the subtle signatures that betray visitors from other star systems. Amateur astronomers are contributing observations through global networks that never sleep. Professional facilities maintain rapid response capabilities that can pivot toward unexpected discoveries within minutes. Before we dive back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. We're no longer passive observers of an empty cosmos. We're active participants in an ongoing conversation between star systems that has been occurring for billions of years. The question is no longer whether interstellar objects exist. We know they do. The question is what they're trying to tell us about the universe we inhabit. Oumuamua's visit revealed that we live in a galaxy where information travels not just as electromagnetic radiation across empty space, but as physical objects carrying actual samples of distant worlds. Every interstellar visitor is a cosmic ambassador bearing news from stellar neighborhoods we can't visit but can now study. Through the materials they deliver to our doorstep, the psychological impact of this realization continues to evolve. We've transitioned from feeling cosmically isolated to understanding that we're part of a vast network of material exchange spanning the entire galaxy. Our solar system isn't a closed system. It's a node in a galactic web of gravitational interactions that regularly delivers visitors. From the cosmic community we're only beginning to comprehend. This connectivity implies responsibilities as well as opportunities. If interstellar objects can carry life between star systems, then our actions in space might have consequences for worlds we'll never see. The spacecraft we launch, the materials we eject, the signals we broadcast, all of these could eventually reach other stellar systems and influence their development. We're beginning to think like a spacefaring civilization, not just because we're developing the technology to travel between stars, but because we're recognizing that we're already participants in interstellar processes, whether we intended to be or not. Every piece of debris we create, every mission we launch, every object we eject from our solar system becomes part of the galactic conversation. The educational implications are equally profound. Students studying astronomy today learn about interstellar objects as fundamental components of galactic evolution rather than exotic curiosities. They develop intuition for processes that operate on timescales spanning millions of years and distances measured in light years. They grow up expecting the universe to be strange, dynamic, and full of surprises. This educational transformation is creating a generation of scientists, engineers, and informed citizens who think naturally about cosmic processes that previous generations could only imagine. The conceptual frameworks they develop will shape how humanity responds to future discoveries and challenges that we can't yet anticipate. The technological legacy continues to expand. The detection algorithms, analysis techniques, and international cooperation protocols developed for studying Oumuamua are being adapted for monitoring potentially hazardous asteroids, tracking space debris, and even searching for technosignatures that might indicate alien technology. But perhaps the most important legacy is the transformation in how we ask questions about the universe. Oumuamua taught us to look for the spaces between categories, objects that don't fit our existing classifications, phenomena that challenge our theoretical frameworks, observations that force us to expand our understanding of what's possible. This methodological shift extends far beyond astronomy. The approach of embracing anomalies rather than dismissing them, of using what we don't know as effectively as what we do, of remaining open to possibilities that challenge fundamental assumptions. These lessons apply to every scientific discipline and every attempt to understand complex systems. Oumuamua's ultimate lesson might be that the universe is both stranger and more comprehensible than we imagined. Stranger, because it contains objects and processes that don't fit our current categories. More comprehensible, because those objects and processes follow physical laws that we can study, understand, and use to expand our knowledge of cosmic evolution. We now live in a universe where every night might bring another interstellar messenger, another opportunity to learn about stellar neighborhoods we'll never visit, another chance to discover whether we're alone in the cosmos or part of a galactic community we're only beginning to recognize. The story of Oumuamua is really the story of humanity's transition from cosmic observers to cosmic participants. We've learned that we're not just watching the universe evolve, we're part of its evolution, connected to stellar processes and galactic dynamics through mechanisms we're only starting to understand. And somewhere out there, right now, the next interstellar visitor is already on its way, carrying information from another star system and perhaps answers to questions we haven't yet learned to ask. The universe will never look the same because we now know it's been sending us mail for billions of years. We just finally learned how to read the return address.